Let's build a 7-segment LED display with 2 digits based on a 74LS90 and 74LS47 and clock it from a 555 dev board. Then we'll use this 2-digit counter to help us draw a winner for the 555 dev board. This circuit has some custom modifications I had to do, both to use it the way I want for this application, but also because I didn't have exactly the parts I needed, so I had to make some adaptations. In general, what this circuit is, we have a clock source going to the 7490 decade counter, which counts in binary up from 0 to 9 and then resets when it's configured like this. Then the count from 0 to 9 is decoded by the 7447 to individually drive these 7 segments, printing out the decimal representation of the binary number. So as we count from 0 to 9 in binary, we see the digit 0 through 9 being illuminated on the display. And if we want to have 2 digits, we cascade another counter, clocking it from the highest bit on the original counter. So the first counter goes from 0 to 9 and back to 0 over and over, and every time it rolls from 9 back to 0, the next counter will increment. The 7490 internally looks like this, and it can do different functions like clock dividing in different amounts, and you can wire things in differently. It has 2 clock inputs and 4 reset inputs, where this clock A goes just to this one flip-flop, driving one of the outputs, and then clock B goes to this network where 3 more flip-flops are controlled. So to use this as a binary counter, we need to take this pin 12 QA output and connect it down to pin 1, the clock B input, so we are cascading the flip-flops as a counter, and our main clock is going to be clock A on pin 14. So that's what we have here. The 555 is clocking pin 14. The A output goes back to the clock B input. For these 4 reset inputs, 2 are called reset 9, 1 and 2, and the others are called reset 0, 1 and 2. And that's because, depending how you have them set up, you'll either be counting from 0 to 9 and resetting back to 0 and continuing, or you can reset the display to show a binary 9 output, or reset the display to show binary 0 output. And here's the function table for the resets. Basically, if at least one of each pair of reset 0 or reset 9 inputs is low, it can be any combination as long as there's one low from each set of resets, you'll be in count mode. So you're going from 0 to 9 over and over. And if you want to reset the outputs to be low, all zeros, you have to set both of the reset 0 inputs high, and at least one of the reset 9s has to be low. This all starts to sound a bit confusing and convoluted. So usually, if this is just set up as a free-running counter, most circuits just take all of these reset inputs and set them all low, which is valid for just counting. But in my case, I need the ability to also go into a reset state where I can set all outputs low, so I need to study this a bit more. I noticed on PowerUp, for both of my digits, both displays are not illuminated at all, and then when we get our first falling edge, the 1s digit lights up an 8, and on the next clock it lights up a 9, and then it resets to 0, and so on. While it's 8 and 9, we have not yet rolled over from 9 to 0, so we haven't cascaded down to clock this one yet, so this is still blank. This is 8 and 9. Then when this rolls over to 0 and we get our first clock falling edge over here, this lights up as an 8, and then this goes through 0 to 9, this advances to 9, 0 to 9, and then finally we get 0, 0. But I want this to just power up in reset at 0, 0, and then automatically start free running a count up through 9, 9 and back to 0, 0. So looking at this function table again, after analyzing all the states and combinations of inputs, I found that using one pin, which is R02, this reset down here on pin 3, if I control this pin between high and low, and if I fix all the other resets so that reset 0, 1 is always high, and then reset 9, 1 and 2 are always low, I can just control this reset 0, 2, high and low, and go between reset outputs and just count. So here's the 1 pin always tied high, 2 always tied low, and I am controlling this pin between high and low on both counters. When I power on, I want this net right here to be high for a while, so it forces this output to be 0, and therefore our display gets a 0 instead of 8 or a blank. To get a high here on power up, I connected an RC timing network between 5 volts and ground, and took the output of the RC network into an inverter. If we assume the circuit has been powered off long enough that this capacitor has discharged, so the capacitor has a voltage of 0, then we power on, it will start charging up toward VCC through this resistor, but in the meantime, with a voltage of 0 or so, the output of the inverter is 1, which, in combination with these other reset pins, allows us to power up with an output displaying 0. Eventually the capacitor charges enough to cross the input threshold from 0 to 1, so the output goes from 1 to 0. And now we are in free counting mode, so we power up with 0, and then everything starts counting properly. The circuit got a little messy, especially as I kept changing it and adding to it, but here's the 7447 and 7490 for each digit, and the inverters to drive the correct display here. It's hard to see it when the lights are on, but currently it's counting from 00 to 99 and repeating. And I dug out my old Jameco breadboard from the 90s, or late 80s, can't remember, and the 555 dev board is clocking the circuit. Since I'm using spare parts, one digit is larger than the other, but it works. So I'll dim the lights and show some of the functionality of this circuit. Right now the circuit is powered off, and the reset input that controls whether we do a power on reset or just let the circuit power naturally is tied low, so the circuit will do its own thing. When I power up, both digits start blank, but then quickly the ones digit will go to 8 and then 9, and then the tens will go 8 and 9 and then kick into 0, 0. So that's not the behavior I want when I power on. I want this thing to power up in zeros. Now I've connected that reset input to the power on reset network, and when I power on, it should start at 0 and start counting. And there it goes. I'll do it several times to make sure. So now we have a power on reset instead of blank and then starting at 8. The other part of the circuit is a 7447 common anode 7-segment LED display driver. There's also a 7448 which drives common cathode displays. The 7447 has open collector outputs, and it takes the 4-bit binary input and converts it into the discrete LED outputs so that it will turn on the correct segments to give you a decimal from 0 to 9. And here's what the internal logic looks like. And here's a representation of the 7447 open collector output. So when a certain segment is not lit, this is open collector, nothing is driving it, and when the output is turned on, this pin is connected to ground. In normal operation driving a common anode display, the LEDs are connected like this. All the anodes are tied together and go to VCC. Each LED has a series resistor. With the transistor being off, open collector, there's nothing connected here, so the LEDs are off. When you turn on a segment, and you turn on the transistor, bringing this pin to ground, now the LED has a current path and turns on. But I only have a common cathode display, so I added an inverter in line with each LED and a pull-up resistor on each input. That way, when the segment is supposed to be off, and this is an open collector, my pull-up takes effect, so I give a high to the inverter, a low on the output, and the LED has ground on both sides, so the LED is off. When the output is supposed to be on and this transistor brings a low to the input of the inverter, we get a high output and the LED segment turns on as required. So I'm converting this common anode driver into a common cathode driver. In order to use this to select a winner for the draw, if I pull the clock, the display will just pause. And when I add the clock, it will resume. So what I'm going to do is speed up the clock so that we can't really see what the count is, but it is going quickly. Then I can pull the clock, and whatever number is showing, that's the winner. So I will take away the electrolytic on the dev board. Now the clock is counting quickly with a smaller value timing capacitor. Now if I pull the clock, in this case 29 would be the winning number. If I put the clock back, pull it again, 90. Do it again, 14. I slowed the clock back down again for demonstration purposes. The only thing is, I don't have 99 or 100 applicants to the draw. So I want this counter to actually stop when it gets to 19. I want it to roll back to 0. In order to make this counter go from 00 to 19 and then reset to 00, what I could do is detect when this tens digit wants to roll over from a 1 to a 2, and then I force this into reset so it ends up really rolling from 19 to 00 instead of 20. So we can detect when the tens digit is changing from a 1 to a 2 by monitoring the QB output, because when we reset and when we go to 1, the QB output is always low. When it goes high, we've rolled away from 19 and we want to roll back to 0, so we look for a high on this output and do something. So I came up with this extra add-on hack. We already have a power-on reset circuit, so I wanted to make use of that. Output B is pin 9, so if I take pin 9 from the tens digit, this will normally be low when we power up or when we're counting from 0 to 19. So this NPN transistor is off and not doing anything. And then when we reach a count of 20, this B output goes high, turns on this transistor, which immediately will short this capacitor to ground, discharging it, bringing the input of the inverter here low, bringing the output high, and resetting this to 00. And when this resets to 00, the B output goes to 0, the transistor turns off, and we have the same condition as a power-on reset. After a short time, capacitor charges up and the counter continues running from 00. So here's the wire coming from the transistor circuit on the QB output of the tens digit. I just plugged it into the power-on reset circuit, so now I'll turn this off. Now this display will roll back to 00 either on power-on reset or when we roll from a 1 to a 2 on this tens digit. So let's power on. We're at 0, and it should count to 19 and then go back to 0. And there it is. So now if I speed up the clock again, when it's going so fast that we can't see, it looks like all the digits are lit on the 1s, and it's going between 0 and 1 on the 10s. So when I pull the clock, it'll stop on a number between 0 and 19. 15. If I do it again, 9, do it again, 18, 7. I'll try to do this in one take to make the whole thing make sense. So we have our counter set up. The clock is this blue wire, so if I take out the clock, it stops on a certain number. Put the clock back in, it continues. Cut the clock, it stops. So that's how we are going to draw a winner. But I need to speed up the count, so I'll take out the electrolytic capacitor. Now it's going so fast we don't know what it says till we stop the clock. I've printed out all the entries here and numbered them, so we'll stop the clock, pick a number, and see who it is. Okay, I will cut the blue wire. 16. Okay, 16 is here. So if the camera focuses, junk from work. Let's see. I need to focus. Hold on. Let me zoom in and there we go. Okay, junk from work. Get in touch with me. Send me a name and address. You can find my email address by going to the About page and clicking for business inquiries. Thanks to everyone who expressed an interest in this project. We may be doing other giveaways as time goes on and we do more PCB projects, so stay tuned. If you're new here, consider subscribing. I'll see you on the next project.